Okay, number 21. Let's look at this function. Okay, if you look at this, going from left to right, it's increasing up to x equals 1. You see that? It's getting the y values, in other words, the y values are getting higher and higher, increasing up to x equals 1, and then it starts going down. The y values start to decrease, alright? So it's decreasing, and it looks like we've got an asymptote at x equals 3, a vertical asymptote. So this apparently never touches x equals 3, but it gets closer and closer to x equals 3 as you keep increasing x less than 3. Alright? Then, if you go x greater than 3, it's increasing, increasing, increasing up to x equals 4. And then after x equals 4, it starts to decrease, it goes down, right? So that's basically the setup. Okay, so now you just put that into interval form. Okay, so it's increasing from negative infinity to 1. And it's also increasing from 3 to 4. Alright, 3 to 4. You're not including 3 because, again, that's a vertical asymptote. Apparently, if x equals 3 in this function, it's probably a rational function, and the 3, if x equals 3, that's going to cause a 0 denominator. Alright, so that would be undefined. So x equals 3 is not in the domain of this function. Okay. Anyway, open interval, so we're not including x equals 3 here. Don't put the bracket because that would include 3, and that would be incorrect. All right. So from 3 to 4, open interval, it is increasing and then decreasing from x equals 1 to x equals 3, but not including those points. Union, and it's also decreasing from 4 to positive infinity. Okay? Okay, number 23. Let's see. Estimate the point or points at which the graph of f has a local maximum or a local minimum. Okay. So, if you take a look at the graph, a local max can be found there. Think of a hilltop. That looks like x equals negative 3. And the value, what does that look like? It looks like it's between 40 and 60 on the y-axis, so that would make it about 50, wouldn't it? So we'll just say 50. Local minimum is right there, x equals 3. And y, what's the y value? That's negative 50. Alright? So the local max, it's also called relative max in older books. Local max is negative 3 to 50. Not negative 3 to 50, it's negative 350. This is not an interval. This is a point, alright? That is the local max. X equals negative 3, y equals 50. And the local minimum, or relative minimum, is 3, negative 50. Now, The book, the edition that I downloaded for this problem was from last summer, that is in 2018, all right, summer of 2018. And since then they may have made changes as far as corrections, all right, in the editions, and I haven't really checked. So your book may have the correct answer here. This is the correct answer. But if you have my edition, the book's answer for the local minimum is 3 and 50. All right, x equals 3, y equals 50. Obviously, that's incorrect. Okay, so if you have that edition and if that's in your book, notify your instructor, okay, that the book's answer is wrong on that. Okay, that is the local minimum. The local minimum in the book's answer is 350, and that's incorrect. Okay? All right, number 25. Let's take a look at this function. We want the local max and min, all right? Well, it says if the complete graph of the function is shown, estimate, okay, the absolute maximum and absolute minimum. So let's take a look at this. So the complete graph is shown, it says. So in other words, see that dot? It's not an arrow, it's a dot, so it ends there. And that's also a dot, so it ends there. So there's not the usual arrow. So it's the complete graph. So the lowest point would be right there, wouldn't it? That's the absolute minimum. Now this point right here is also a minimum. It's a local minimum. You could call that a local minimum as well, because there is a neighborhood which has that, an open interval which has that in it. And it's the lowest point in that neighborhood, right? But it's the absolute minimum as well. Okay, so that's a local min, and that's a local max, and apparently that's the absolute max. It's the highest point on the whole thing, right? So there you go, all right? The absolute min would be, looks like x equals -8, and y equals, what, about 225 roughly? -225. Looks like it's about halfway between -200 and -250. Alright. And over here, x equals, looks like about 7, right? 6, 8, so between those two, 7. And y is 150. Alright. So, let me write these down for you. Absolute max would be 7 and 150. And absolute min is -7.5, -225. Okay, now the book's answer, if you have my edition, which I downloaded summer of 2018, is -7 for the absolute min, that is, is -7.5, -220. Now, okay, so if you look at this y value on this absolute min, look at that. Yeah, it's not quite halfway down between -200 and -250, but you know, you could call that -225 and probably get away with it. All right, because these graphs are not super spot on, you know, the way they print these, and I mean, you can go crazy as far as measuring and all that stuff. Finding the exact coordinates, all right, you would need something bigger than this graph. This is a tiny little graph in your book. All right, and so I know you could zoom in and all that, but if I were grading this on a test and you put negative 225 as the y value there, I would not take off any points. That's just me. Your teacher might. All right. If they insist on negative 220, well, what can I say? That's your teacher. All right. But I would give it a little leeway, because there's you know, there's a little bit of an error factor here because of the drawing, the limitations of the drawing. So I think I would give the student a benefit of the doubt if they're, you know, kind of close to the point that we're talking about. So obviously if you put negative 200, that's obviously it's not on negative 200 there. If you put negative 250, the same thing. All right, but that's kind of a judgment call for a teacher. All right. Now if you put negative 225 and you got marked wrong for that, I would take it to the teacher and try to state your case. All right. You could say, Professor, you know, it's pretty close to halfway across, and these drawings are not super duper accurate. All right. So, and it's kind of hard to figure out exactly where that is. So would you please give me full credit on this? I mean, I was pretty close. And if your teacher is a reasonable person, I'm sure he or she will let you have that point. Okay? All right. And if you want, show him or her this video, and I'm going to say, Professor, please have a little mercy, okay? From a fellow teacher. All right? Okay. Okay, problem 27. Table 4 gives the population of a town in thousands from 2000 to 2008. What was the average rate of change of population, part A, between 2002 and 2004, and part B, between 2002 and 2006. So if you look at the chart, can I get that all in there? It's kind of long. The year would be your X values, and the population would be your Y values. The population depends on the year, so the population would be the dependent variable, the year would be the independent variable. All right, so if you were to plot this, the year would go on the x-axis and the population would go on the y-axis. So this will tell you what x2 and x1 are. All right, that would be the dates. And f of x2 and f of x1 would be the population. All right, what's f of x? Well, that's basically given as ordered pairs. All right, remember, a function is a set of ordered pairs. Okay, so here we go. Part A. So f of x2 minus f of x1. Well, wait a minute. What are x2 and x1? It says between 2002 and 2004. So x2 is 2004 and x1 is 2002. So what's f of x2? That would be, what's the population in 2004, right? That would be 77, or really it's 77,000. It's in thousands, right? So you write 77 minus f of x1. What's x1? It's 2002. What's f of x1? That would be the population in 2002, which is 83. And then you go x2 minus x1, so that's 2004 minus 2002. Alright, so if you punch that into your calculator or just figure it out, you get -3. Okay? So again, this is in thousands. These are all in thousands, all right, up here on top. So that means the average rate of change between 02 and 04 would be minus 3,000 people per year. Okay? In other words, they're losing people. Losing people. It's negative. Alright, so B, part B. Again, we've got 2002 and 2006, so X2 is 2006, X1 is 2002. So what's population in 06? That would be 78, so there's your f of x2, 78, minus f of x1. What's, let's see, 2002, the population is 83, so f of x1 is 83, over, and then 2006 minus 2002. So that's negative 5 over 4. Okay, or getting a decimal equivalent, that's negative 1.25. So this is again in thousands. If you multiply that by 1,000, you'll get the exact figure. It's negative 1,250 people per year. All right, there you go. Number 29. For the following exercises, find the average rate of change of each function on the interval specified. So we have h of x is 5 minus 2x squared on the interval negative 2 to 4. So alright, so h of x2 minus h of x1, that's going to be h of 4 minus h of negative 2 over x2 minus x1. So that's going to be 4 minus negative 2. Alright. So plug in 4 in h of x right there. So you're going to have 5 minus 2 times the number 4 squared. So there's h of 4. And then subtract h of 2 from that. Put that in brackets because you want to subtract both of these terms here. So we've got 5 minus 2, and x would be negative 2 here. Square that. All over. Minus a minus is plus, so 4 plus 2 is 6. Alright, moving over here so I can have some room. So we've got 5 minus 2. And 4 squared is 16. So 5 minus 2 times 16. Watch your order of operations. Once again, you do the powers before you do any multiplying or adding or subtracting. Okay, so you wouldn't go 5 minus 2 is 3 and so on like that. Alright, you have to first square this and then you have to multiply. And then you can finally do the subtraction. Okay, and so here we've got 5 minus 2, again order of operations, watch out. Negative 2 squared, that's 4. Negative 2 times negative 2 is positive 4. All over 6. So that equals 5 minus 32 minus, and then you've got 5 minus 2 times 4 is 8, so 5 minus 8. That's still in the parentheses or brackets. So don't leave those off because you're going to subtract those two terms, and that's over 6. So 5 minus 32, and then minus 5 plus 8. The minus in front here makes that a plus. 5 minus 32 minus 5 plus 8. All right, that equals negative 24. All over 6. And negative 24 over 6 is negative 4. So there you go. Okay, number 31. We have g of x equals 3x cubed minus 1 on the interval from negative 3 to 3. So we have g of 3 minus g of negative 3 all over 3 minus negative 3. Alright, so let's get g of 3 up there. That's plug in the 3 right there. So you've got 3 times 3 cubed minus 1. There's g of 3. And then subtract g of negative 3. So that's going to be 3 times negative 3 cubed minus 1. All over 3 minus a negative 3 is plus 3, right? 3 plus 3. Minus a negative is plus. So 3 plus 3, which is 6. Alright. So this is 3 cubed. 3 times 3 is 9. 9 times 3 is 27. So you've got 3 times 27. And then minus 1 minus, and here we've got negative 3 cubed is negative 27. Negative 3 times negative 3 is positive 9. Positive 9 times negative 3 is negative 27. So 3 times negative 27 and then minus 1. Pardon the nested parentheses there. Probably should have used brackets, but that's alright. Okay, 3 times 27 is 81. And then this is negative 81 minus 1 inside the parentheses. Negative 81 minus 1 over 6. And so we've got 81 minus 1 is 80, and minus, this is negative 82, so minus a plus. Minus a minus is plus, so this is going to be 80 minus negative 82, so that becomes 80 plus 82. Over 6. Alright. And so that's 162 over 6. Which is a nice integer 27. There you go. Okay, we have number 33, and p of t is a rational function. Let me write this down. P of t is t squared minus 4 in parentheses times the quantity t plus 1 over t squared plus 3 on the interval from -3 to 1. Okay. So we've got p of 1 minus p of -3 over 1 minus -3. So I have to write this a little bit smaller because of this complicated function here. Alright, so what's p of 1? You put a 1 here, here, and here, so you're going to have a fraction. So it's going to be 1 squared minus 4. 1 squared minus 4 times 1 plus 1 over 1 squared plus 3. Now, fortunately, 1 is not too hard to evaluate here, so that one's not too bad. Minus, okay, once again, what do we have here? We evaluate at t equals -3, the same function, so you've got a -3 here, here, and here. Alright, so you've got, let's see, let me use brackets. You're going to use a -3 and square that. Minus 4. And then I'll use parentheses here, -3 right there, plus 1. Over -3 squared plus 3. Now we're not done yet because we still have the denominator of this average rate of change to worry about. So 1 minus a -3 is 1 plus 3, which equals 4. So I put all of this over a 4. Like that. Alright, move over here to get some room. Okay. So this becomes 1 squared is 1, 1 minus 4 is -3. This is 1 plus 1. Oh my goodness, what is that? Oh, I think it's 2, yeah. It's probably one of the first arithmetic facts I ever learned. 1 squared is 1 plus 3 is 4. So 1, let's see, that's 4. And then you got minus. And so we've got -3 squared is positive 9. And then 9 minus 4 is 5. So we've got a 5 there. And then -3 plus 1 is -2. Over -3 squared is positive 9. And 9 plus 3 is 12. Alright, and that's all over 4. Okay, so got negative 3 times 2 is negative 6/4, so you got negative 6/4, or you could cancel here the 2 with the 4, so that becomes a 1 and a 2. You can cancel this as well, that becomes 1 and that becomes 6. Alright, so we could do a little simplifying. That's negative 3 times 1 is negative 3 over 2 minus, then you've got 5 times negative 1, don't forget that's a negative still there. 5 times negative 1 is negative 5, and that's over 6. Alright, over 4. And that's equal to, we've got negative 3/2, and this is a minus a negative, right, which is positive, plus 5/6 all over 4. Okay, and let's just do the top ones. We're going to take care of the top one by getting a common denominator. That would be a 6. Alright, so let me take it over here. Okay, so that equals negative 3/2. In order to get a 6 here in the denominator, I have to multiply that by 1. I don't want to change the value of that fraction, but I do want a 6 in the denominator. So to do that, I would need to multiply that by a 3. But in order to multiply by 1, it would have to be 3/3. So I multiply this by 3/3. Again, you're multiplying by 1, so you're not changing anything really. And you can maintain that equal sign. Alright, and then plus 5/6 all over 4. So that equals a negative 9/6 plus 5/6 over 4. And that equals negative 9 plus 5 over 6 over 4. So since these two fractions have the same denominator, I can just add the numerators together over that denominator. Alright, that's what I do here. That's what I indicate here. So here I've got negative 9 plus 5 is negative 4/6. Over 4 over 1, right? That's 4 over 1 is 4. Flip the 4 over 1 over and multiply by the negative 4/6. Negative 4/6 times 1 over 4. You invert the bottom fraction and multiply by the top one when you do these complex fractions, and you can cancel the 4's out. So you get a negative 1/6. Negative 1/6. That's the answer. That's the exact answer. Alright. Now, your book has a decimal approximation. Negative 0.167. That's negative 1/6 as a decimal, but rounded to 3 places. Alright. So, personally, I prefer this because this is the exact answer, and it's easy to get the decimal equivalent for this in a calculator. If you're an engineer, you've probably memorized some of these decimal equivalents for common fractions, commonly used fractions, and so it's always better to keep the exact answer if at all possible. That way you can round to as many places as you wish. Okay, but if you give your result as 0.167, you need to indicate that this is an approximation rounded to so many places. If you just gave it as 0.167 without those conditions listed or given, you might assume that's the exact answer, you know, which it isn't. It isn't. So always use the exact answer when you can possibly use it, if it makes sense to you, okay, in a practical way. Of course, if you can't, you can't, but you should specify that this is an approximation. All right, and that way there won't be any you know, mistakes in construction or whatever you're doing with this number. Okay. End of sermon.